Welcome. Today, we're going to tackle a core question in engineering and physics. When you have a whole bunch of different forces all pulling on one spot, how do you figure out their single combined effect?
Right. So imagine a tug of war, but with ropes pulling in all sorts of different directions from a single hook. What's the actual total pull, and which way is it really going? Well, that's the exact puzzle we're going to solve today. So, this single equivalent force has a special name, the resultant. And finding it isn't just some academic exercise. It is absolutely essential for everything from making sure a bridge can handle wind and traffic to calculating the lift on an airplane's wing.
We're going to break this all down in 5 parts. We'll kick things off with a simple visual method. Then we'll level up to a much more powerful analytical tool. And finally, we'll put it all to the test with a solid example from our source material.
All right, let's start with our first tool. It's a graphical method called the parallelogram law. And honestly, it's a fantastic way to actually see how forces combine. So what does all that really mean? Well, it's pretty simple. If you draw your two forces as two sides of a parallelogram, both starting from the same point, the diagonal that cuts right between them, that's your resultant force. And this illustrates it perfectly. See? You start with forces P and Q. Then you construct the rest of the parallelogram just by drawing parallel lines. That diagonal, the one labeled R, that's your resultant force. It tells you both things you need to know: the magnitude, so how strong the total pull is, and the direction.
Now, this visual method is pretty awesome for 2 forces. But what if you have 3 or 4? It becomes really tedious, really fast. You'd have to find the resultant of the first 2 forces and then combine that resultant with the third force, and so on and so on. It just gets messy.
So, we clearly need a more powerful method, one that can handle any number of forces. And that brings us to the method of resolution. This is the real workhorse for engineers.
The beauty of this method is just how systematic it is. I mean, instead of drawing shapes, we use some basic trigonometry to do one simple thing: break every single force down into its horizontal, or X, and its vertical, or Y, parts. Then we just add up all the X's, add up all the Y's, and combine them back together for our final answer. It's a clean process.
Let's actually see this method in action with a concrete example from our source text. Our mission, should we choose to accept it, is to find the resultant of these 4 forces acting on this one particle, P.
Okay, so here's our setup. We have 4 forces pulling on point P from all different directions. Now, 2 of them are simple. One's straight up, one's straight down. But the other 2 are acting at angles. Our mission is to break all of them down into their simple X and Y components.
But hold on, before we start crunching numbers, we have to agree on directions. We're going to use the standard system. So anything going to the right is positive, left is negative. Anything going up is positive, and anything going down is negative. This is super important to get the right answer.
Okay, first up, let's sum all the horizontal components. We call this sigma Fx. So the 300 Newton force has a component that's pulling to the right, so we use cosine and it's positive. The 400 Newton force, its horizontal component pulls to the left, so that one's negative. The other 2 forces are purely vertical, so they have 0 horizontal component. The math gives us a net horizontal force of 199.3 newtons. Next up, we do the exact same thing for the vertical components, our sigma Fy. We've got 500 newtons pulling straight up, so that's positive. 250 newtons pulling straight down is negative. The 300 Newton force has a downward component, that's negative, and the 400 Newton force has an upward component, which is positive. You add them all up, and we get a total vertical force of 657.8 newtons.
Awesome. So we've just boiled down those 4 kind of messy forces into one simple horizontal force and one simple vertical force. The hard part is totally over. Now we just need to combine these 2 to find our final answer.
To find the magnitude, the overall strength of our resultant force, we use a familiar friend, the Pythagorean theorem. Yep, that's right. We're just finding the hypotenuse of a right-angled triangle made by our total X and Y forces.
And when we plug in our numbers for the total horizontal and vertical forces, the math gives us a final resultant magnitude of 687.4 newtons. That number represents the combined strength of all 4 of those original forces. So what about the direction? Well, for that, we use the tangent function. The tangent of our angle, theta, is simply the total vertical force divided by the total horizontal force. The calculation gives us an angle of 73.1 degrees,
and that's the angle that the resultant force makes with the positive horizontal, or x-axis.
And there it is, the final result. All four of those initial forces acting on that particle can be replaced by this one single resultant force of 687.4 newtons acting at an angle of 73.1 degrees. And it has the exact same effect. Now that is the power of this method.
So after all that, what are the most important things to remember? Let's do a quick recap of the key takeaways here. The most crucial thing to walk away with is this. By breaking down a complex problem into simple x and y components, we can solve it systematically and accurately, no matter how many forces are involved. It really is a foundational skill for any kind of structural analysis. And that leads us to our next big question. What happens when all the forces cancel each other out perfectly, so the net force is zero? Well, that concept is called equilibrium, and it is the absolute foundation for designing any structure that's meant to stand still. We'll be diving into that next time.